Good morning. It's a great pleasure and an honor to be here. And wow, yeah, I want to say just after the excellent introduction that we've had from Ben Movsad, I'm part of Wayne State University, and we're like the other operation, and we're part of the Karmanos Cancer Institute, which is a NIH Comprehensive Cancer Center. So we actually collaborate an awful lot with Henry Ford, and just getting this worked out here. How do I move? The green button, right? Okay. And so the objectives that I've got in here in this presentation is to tell you about the key radiobiology underlying hypo-fractionation without going into too much of a deep detail, but really to point out how and where we can use this radiobiology to guide the clinical use of hypo-fractionation. And when we get to the end of this, what you're going to see is that there's an awful lot of questions that we still haven't answered yet. And conflicts of interest, I don't have any conflicts of interest, and I thankfully never will, I don't think. There's just one interesting little thing, ibpro.org. So the only conflict of interest that I've got is that I'm funded by NCI, and can't really complain about that. But please, all of you, consider attending IPRO, the IPRO course, next May the 6th to the 11th. And obviously you can just look it up right now and see what's going on, and you will be amazed to find out that we actually pay you to attend the course. What? Yeah, I know. It's almost unbelievable, isn't it? Thank you so much to the NCI. So, historically, our research has always focused on that low dose range, hasn't it? And so, you know, we know all about the radiobiology. You can read books about it. There's been much less incentive for actually funding the high dose research, and until now. So why? Well, the answer is because we can. The physics has allowed us to do things now that we couldn't do 30 years ago. And that's absolutely key. No way could we be even considering. I mean, you can't be giving 18 gray per fraction with parallel opposed fields, for goodness sake. I mean, it's obvious. You guys know this. Patient convenience and demand. I mean, hard to go back now and offer a patient, 30, 40 fractions when the possibility is to do it in a third of that. Potentially lowering the whole cost of treatment, but let's be careful there, because we've got to put more into the planning and the monitoring of the treatment when we're giving such precise doses. A lot of evidence, as we're going to be finding, that these treatments can be very effective, and part of that is that we have evidence of a low alpha over beta in some tumors, like prostate and breast, and we got a big question against other tumors. And I'm fond of throwing out esophagus, melanoma, liposarcoma, even GBM and pancreatic as possibilities that in the next 20 years we're going to be taking a look at. But I can't give you the answers. Right, just a bit of a sidestep. I'm going to show you this. It's a paper that we published in radiation oncology as a result of an ICRU operation, and it defines EQDX, equivalent dose in X gray fractions for a particular alpha over beta, right? And that's the formula. You can use that formula in your head. What's the point of this? The point is not to use BED. How many of you use BED all the time, right? Oh, that's good. Not so many. Excellent. Okay, so maybe I'm bringing coals to Newcastle here. We don't worry too much. So that's the formula for EQD2. So you take any dose per fraction that you have here and convert that into a total dose that would be given in 2 gray fractions. So there's your 2 gray fractions, and you have to choose an alpha over beta. Now the point about using this rather than BED is that if we use BED, then as alpha over beta starts getting low, then BED can go infinite, right? Obviously, if I put alpha over beta approaching 0, then BED goes infinite. And BED starts getting rather silly, isn't it? I mean, quick example here that I'll spend very little time on. If my chord alpha over beta is 2 gray, and I'm giving 4 times 5 gray to that chord, the EQDT works out to be 35 gray. Boom. and you go to Quantec and you look up the tolerance dose for cord at 2 gray per fraction is 50 gray. Okay, fine. Use a BED and you calculate a BED of 70 gray. What on earth does that mean? All right, I think you get the message, don't you? So I just thought I'd sidestep that, and it's even now as common that you can look up the textbooks to get all that information. Just to rub that home, half a gram of potassium in a banana, that's 15 becquerels of radioactivity, isn't it? It's not an awful lot. I mean, every time you eat a banana, you eat 40 nanocuries. The point is that if you actually look that up on the web, BED stands for banana equivalent dose, not for biologically effective dose. So there you go. Don't use BED. Please let's get away from that. So why not use the linear quadratic model at high doses per fraction? And there's a lot of discussion about this, about the response is not linear quadratic. This is in the literature, huge arguments. I'll allude a little bit to that later on. I don't think the issue is resolved, because clearly it's not just straight target cell killing. I mean, we had the possibility of increased apoptosis. I'm not going to spend any time at all on that. But increased vascular damage, increased immunological effects, and Brian Marple's sorry, I have this terrible problem. Steve Brown, sorry Steve, I do apologise. They're going to come along afterwards and elaborate on some of these more specific effects. And also, obviously in any malignancy, we know that we have mixed populations of cells with different response characteristics. So all these can serve to modify the actual response that we see in terms of total dose against dose per fraction. And clearly, the way that that's done is going to depend on the tissue type and the tumor type and the stage. What I'm not going to spend any time on, apart from this one slide, is just to point out that obviously hypoxia is a big deal. And my friend and colleague Bert van der Kogel has been involved in this for many years. This is one of his beautiful slides here, showing that the variation in hypoxia throughout a tumor here, and the vessels are marked in white. They're stained with CD31, and you've got Herc's 33342, which is a measure of perfusion. So you can see anything that's got the blue here is obviously a perfused vascular structure. And you've got two hypoxic markers that he injected at different times. You've got the one that's brought up in green and the one that's brought up in yellow, and he injected those with a 2-hour gap between them. And what you can see here is that in many places those overlap and produce yellow. Green plus red is yellow. But in other places you can see either the red marker alone here, or you can see the green marker alone. So what this is illustrating very clearly is that hypoxia in a tumor changes dynamically. And the reason why we need to be aware of this is that when we're giving, let's say we're giving 3 times 18 gray, it's almost impossible to believe that hypoxia is not going to be some sort of issue right at those high doses per fraction. It's something we've learned to overcome when we're giving 2 gray per fraction, 1.8 gray per fraction, 2.5 gray. Because we give so many fractions. But once we start getting down to 3 or 4 fractions, we've got to keep these factors in mind. But I stress, still no evidence, one way or the other, as to how that hypoxia is going to affect that situation. So really going right back to 1982 here, Howard Thames, Rodney Withers, Lester Peters were the people that constructed this original whole framework, in where you plot a total dose for an iso-effective response in the tissue against the dose per fraction. And all these, what they deliberately did is remember to plot that dose per fraction axis from high to low, because that means that if you go away and get the lines, they all run from the bottom left to the upper right. And clearly the slopes for the early reacting tissues are more shallow than the slopes for the late reacting tissue. And this was a very clear identification that we expect more fractionation response in late reacting tissues than we do in early reacting tissues. And within the context of the tumours, at the time, we kind of largely believed, and I think based on head and neck and based on lung, that those responses would be like the early responses. So hyper-fractionation would be something that you would want to do in a tumor system, like say a lung or a head and neck, in order to achieve a greater differential with respect to the late reacting tissues. So in other words, you know, the vertical displacement is more in that situation if you go to lower doses per fraction. But now the whole paradigm has changed, hasn't it? I mean, it's just almost like every site that we're thinking of now, because the physics has opened up the possibility now of safely doing hypo-fractionation. So it's almost like every time we're asking now, and we're even going so far as to be asking, as I'll allude to later, in head and neck cancer, whether there's a possibility that we should be hypo-fractionating because, you know, I'll explain it later, possible subpopulations in head and neck cancer that may individually respond better to hypofractionation. So clearly that is the answer, that we're better here now because the gap can be more down here at high doses per fraction. So from a biological standpoint, you can see that any time that we are showing that there's a low alpha over beta ratio present in a particular tumor type, site, stage, whatever, then is a good biological justification for doing hypofractionation. Now, our thinking has been based now since that 1982 paper largely on the linear-quadratic model, and what I've done here is I've plotted that in terms of a cell survival curve here, you know, ensuring that we go all the way down to 10 to the minus 9. You know, how many potential target cells in the tumor? 10 to the 9 per gram, right? So this is where we need to get down to achieve local tumor control levels. So that's just a very simple curve, and I've done this on the basis of an alpha over beta value of 3 gray and a surviving fraction of 2 gray of half. You know, so I've already assumed here that we're talking about maybe a tumor system which is kind of like a prostate and a breast, rather than maybe like a head and neck and lung, on the face of it anyway. So let's look. There's 17. That's 12.5 gray. I'm going to take a tangent to that curve, right? Hell, you're all physicists. You can differentiate a linear quadratic curve in your head, and that's what you get. So the effective D0, or the effective slope of that curve, is 1 divided by alpha plus 2 beta D. So calculate those numbers. Come up with a table, as I've done here. So surviving fraction at 2 gray, 0.5, bit more resistant, 0.6, bit more resistant, 0.7. Alpha over, series of alpha over beta values for each, and you know, we know that we're going to be down here for things like prostate and breast, and this will be the dose per fraction. What do we got here? Everything in yellow is where that effective D0 value is less than it would be for ataxia telangiectasia cells, the most sensitive human cells that we know, cells that virtually do no DNA repair. So what does this mean? It means quite simply that we cannot pretend that the linear quadratic model can possibly be valid out at those very high doses per fraction. What's going to happen is that the LQ model is always going to overestimate the effect. Now that's good because it means that it's going to underestimate tolerance doses. So we're in a kind of safe haven, if you like, a safe direction. But we've always got to remember that if you calculate stuff according to LQ, you're potentially going to underestimate effect, right? Which is good from the point of view of tolerance, but in terms of the prescription that you're using for a tumor, you might want to think a little bit about that. So that's how all that's working. So in other words, the LQ model must straighten at high doses, and you guys know from reading the physics journals that there's been so much activity in modifying that LQ equation to figure out how we might do that. One of the simplest ways is, instead of using a linear quadratic model, is to use a linear quadratic cubic model. And quite simply what we do in the LQ, I use the same parameters as we had in that earlier one. That's the LQ model. And so what I've done here is I've constructed a linear quadratic cubic model, which, as you can see here, now has an additional term, a negative term with a negative cubic term with a constant of gamma. Now, I do hope that you're all 3 steps ahead of me, because it's quite early in the morning and you've had your coffee, right? And so you know what's going to happen if this dose keeps increasing and increasing, right? this is going to bend over and come up there, isn't it, at some point? And so this is the simplest possible modification that you can make to the LQ model, but it's quite clear that, as with all of the other modifications that you're reading about in the physics journals, to try to get more, let's say, linearity up here at the higher doses, this is only going to be valid over a certain dose range. So what's also quite interesting here is that if we look at a dose between 5 and 6 gray, the way that I've set this up in this particular example here is that if I magnify that, you can see that's deliberately where the LQ model starts to deviate from reality, let's say, out between 5 and 6. So often we say that we're on very safe ground using linear quadratic between 1 and 6 gray per fraction, right? Still got to worry below 1, and I'm not going to go into this here. We have to worry below 1 gray per fraction because of low-dose hypersensitivity, right? And if anybody didn't ever believe low-dose hypersensitivity, for goodness sake, go back and look at the paper we published in the Red Journal earlier this year, where we've seen it with the cytogenetic responses. So that's the end of that story. It exists, period, right? So do go and look that paper up. So that's where we are here now, and gamma, what I've done here is deliberately chosen gamma so that this curve is linear here at a dose of, in this particular instance, 18 gray. And, I've done that because of 3 times 18 gray that we're thinking about in terms of a nice hypo-fractionated treatment that we tend to be converging on in lung, for example. Now, again, this is aimed squarely at you guys physicists, and for goodness sake, I know nobody's going to admit to never reading Stanley Curtis's 1986 paper because it is an absolute classic. But just privately, if there are any of you, maybe the younger generation, who've never seen that paper, for goodness sake, go and look it up. And it's beautiful because it does reconstruct exactly that dose response survival curve that goes down and then starts linearizing. So it's kind of linear quadratic at low doses per fraction and then straightens out at high. And it's really an elegant solution because you start with, I'm not going to go into it in detail, you start with viable cells here, and they can obviously be given lesions here, which are complex lesions which would directly contribute to cell death, or they can be potentially lethal lesions, repairable lesions, and the easiest thing to think about is those are the more simple double-strand breaks. And they can either be correctly repaired, but if there are too many of them, you get binary misrepair because you get overlapping of the repair complexes, which would be particularly the case in homologous recombination. So what we've got here is a situation where you can imagine those are the complex double-strand breaks which allude to the alpha value in the LQ, and these are the simple double-strand breaks which are alluding to the beta value. But hell, this has got 4 parameters. They say that you can fit a nice one-humped camel, you can fit the response with 2 parameters, right? Double-humped camel, you need 3 parameters. With 4 parameters, you can make it walk. And the point being that this is a really elegant model, but any attempt to put this onto clinical data will mean the uncertainties on the values of these parameters are large enough to make it completely useless. And that's why still, with all of this discussion about making these models more complex, we still like to use the linear quadratic model as much as possible, because it means that we can get decently small uncertainties on the parameters to enable us to make clinical decisions based on those data. So what about response heterogeneity? Alternative damage response pathways and cell types which are dose dependent. And I know that Brian and Steve are going to refer to some of these, so individually I'm not going to spend much time on this. But vascular effects clearly occur more often and more clearly at higher doses. And this is a lovely review paper by Park in Radiation Research a couple of years ago. And what they've done is they've taken rat tumours here, Walker 256 rat tumours here, and they've measured the functional intravascular volume here as a function of the size of the tumour for for either controls or after exposure to different doses. And what you can see interestingly is that a 2 grade, which would, let's say, 2 grade per fraction, it doesn't change anything, right? The dashed line is the control line reproduced here. So either looking at the vascular volume 2 or 6 days, it's basically the same as the controls. But once you start going up to higher doses, and that would be then higher doses per fraction, you can immediately see reductions in the functional intravascular volume. So in other words, what we're saying is that vascular effects are a feature that's going to modulate the response for high doses per fraction that it doesn't do at 2 grade per fraction. And so immediately you've got, let's say, a non-targeted, non-direct tumor cell targeted response, which is feeding into the response here that we've obviously clearly got to take account. And again, in that Park paper, he alludes to breast cancer patients where they took the endothelial cells, in other words, the structural vascular cells from normal breast or cancers, and showed actually different sensitivity and responses in two of the patients here. This wasn't a very big study, but clearly there was evidence that in the cancer cells, the endothelial cells, the vascular endothelial cells, are more sensitive to radiation than they would be in the normal breast. So again, that's a way in which we can access more of an effect on the malignancy, in this case the breast malignancy, by giving high doses per fraction. That's kind of how that's working. And work that we're doing in our labs here, led by Gally Hillman at Wayne State, and this was published recently, emphasizing, Gally's developed this wonderful technique of growing human tumors in all of the different organs in mice, and these are particularly some lung studies. So she's grown the A549 non-small cell lung cancer in the nude mice, and this is what it looks like 27 days after giving 12 grade rate of radiation. And what she's done here is compared the tumor with a normal lung here. And what you can see here is these small tumor nodules here, degenerative changes, large vacuoles, hemorrhages, scattered inflammatory infiltrates, all of these things that are not necessarily associated with direct malignant cell kill. And the lung is fascinating because it's a very immunogenic organ. So if you are looking for immunological effects, then the lung is a good place to start. And you can see here in the normal lung, you've got heavy infiltration of inflammatory cells, lymphocytes, neutrophils, fibrous tissue, and you can see that this here, the extensive fibrous tissue here, that's been stained beautifully blue with the Masson trichrome. So you can see immediately that any time that you're going to be giving these large size doses per fraction, you're going to need to be considering these non-direct malignant cell killing effects, particularly these inflammatory responses here. And this is 50 days after 10 gray, and you can see here, just looking at damaged blood vessels in the controls here, you can see it's 29%, and in the irradiated it's 42% here. And you've got disruption again, disruption of basement membranes, thickened inflammatory hemorrhagic septa. So it's quite obvious from looking at these beautiful pictures that these non-tumor cell targeted effects are going to be very important to evaluate. And I know that Brian Marples and Steve are going to be coming on after that in order to give you a better view on that. And here's to do with the immunology here. You can see changes in 4 factors there: IL-6, TNF alpha, and the IL-1 beta and interferon and gamma there. And in this case here, you can see that the addition of a very simple compound, natural compound, soy isoflavones, can actually reduce these inflammatory responses, or these change the responses that you see in terms of the normal upregulation of these cytokines. So, we've been looking at the possibility that you can use soy isoflavones as a very easy, nobody's going to question the use of these things. We've got clinical trials going. It's already been approved, FDA approved for doing this, no problem whatsoever. But I'm going to take a very cynical view as somebody that is not part of a pharmaceutical company and never will be in my whole life, even if I'm dragged there kicking and screaming, I'll run for the door. And the pharmaceutical companies will never touch this with a long pole, because they're never going to make any money out of it. Boom. So there you go. That's why I can't ever be part of that group of people. So, response heterogeneity, mixed target cells with different radiation sensitivities. And again, I mean, it's all there. You go back to it. Timothy Schultheis published this beautiful modeling paper back in 1986 or 87 here, actually 1987, you can see at the top there. And there may even be some of you in the audience that weren't even born then. Dare I say it? No, that's probably a bit extreme, isn't it? But anyway, but this again is a paper that's worth getting and reading. And basically what Tim showed here is that these possible higher order terms, for example, in the linear-quadratic cubic model, can result just from response heterogeneity. That's all. You know, a tumour is not a uniform cell population. It contains different populations of cells, even the tumour target cells themselves, you know, disregarding the vascular responses and everything. And this in itself can lead to an increase in the measured value of alpha over beta, which can lead to an effective linearization of the underlying cell survival curve for these target cells, and explaining why we can see these higher alpha over beta values certainly for early reacting tissues, but also in some tumours, maybe like head and neck and lung cancer, right? And okay, here's a model that I ran up. You know, I just opened up my copy of Mathematica and did this, so you guys can all play these games as well. And I assumed that we had a tumour population, a clinical tumour population, 30% that were intrinsically more resistant and 70% that were intrinsically more sensitive, right? But they both have the same alpha over beta value. I gave them the same alpha over beta value of 3 gray, right? And I assume this population, the 30% in blue, was more resistant than the red. Where do you think this idea comes from? Oh my goodness. HPV negative and HPV positive head and neck cancers, right? Boom. So you mix that clinical population together, as we have done in the past before we realized that we have this distinction with patients that walk through the door now, and you effectively clearly get a, let's say, a cell survival curve that is more linear than either of these two. Now, if I transfer this to plotting the reciprocal of the dose against the dose per fraction, then here's where you can see that the alpha over beta of 3 gray is where these individuals extrapolate back. But this would be that relationship for the black line, for this line. So if I quite straightforwardly put a line through that black and just extrapolate it back here, I've got an alpha over beta of 20. So I start off with an alpha over beta of 3 for the individual tumour populations, the individual tumour types. I now end up with 20. All right, so you're going to say, well, what about, you know, it's kind of bending over, so let's consider this over a larger range of dose per fraction here. So it kind of comes up, kinks over a bit. But then if you try to fit a straight line through here, then it's still coming out at 10. Oh, wait a minute, that's interesting. 10 is the value that we normally accept for alpha over beta for head and neck cancers, isn't it? So you can see how it's quite easy to be misled, that although in the whole clinical population you may be ascribing a high alpha over beta value to head and neck or lung cancers, if you actually were and are able to dissect out in more detail the molecular characteristics leading to the individual clinical subtypes, then each of those may well have a low alpha over beta. And where are we going here? Oh my goodness, we're kind of talking in terms of giving hypo-fractionation or SBRT for everything now, right? Everything in the human body, if we step this logic further and further. Now, I can't say that for sure because we just don't know the answers yet. We won't have the answers for another 10 years, 15 years, when we've analysed more clinical data to determine whether what I'm saying is just a wish or a dream, and whether it's actually going to come true. And this then leads me to highlight this debate where Martin Brown and David Brenner in particular, every 5 minutes you see another paper from David saying there's nothing wrong with the linear quadratic model at high doses per fraction, right? And this was a paper that was published last year. And you know, for goodness sake, go and read these. They're really worthwhile reading. But in a nutshell, and I quote this one, this particular date, they say LQ applies at high dose per fraction. Boom, all right? Why don't we all just go home and not bother doing research anymore? Well, luckily, 3 months after that paper was published, just 3 months after, and so this is now a 2000 and oh no, this was 2013. So right before that Brenner paper was published, so Brenner didn't actually knew that this one was coming down the line. This is a paper published by the father of the linear quadratic model, Howard Thames himself, and then Rodney Withers. Oh my goodness, you know, you don't argue with these guys. They invented the linear quadratic formulation virtually in relation to fractionation response. And what was their conclusion from this paper? Consistent with using LQ to estimate tolerance doses will lead to underestimation of those tolerance doses. Boom. So there you go. And look at that last line there taken out of the abstract. Possibility that the survival curve, target cell survival curve is increasingly linear with increasing dose. Exactly what we've been talking about right at the beginning here. So there's no finalization to this argument yet. It's going to keep going on and on and on, I promise you, because this can only be settled when we have much more clinical data than we have on the responses to high doses per fraction. But you know, you can see how these are great research questions to set up. Again, this is an analysis that Thames et al., who was the first author here, did in this paper, and they looked at, it was kind of a curious combination. It was either giving the control grade, this is in the guts here, and 14 grade that could either be as a single shot here, or it could be 4 plus 10 or 10 plus 4 or 7 plus 7. And so in doing that, if you plot the surviving number of cells per gut circumference here against the size of the first dose, then you're going to see a pattern that looks like this. And what they concluded here, and I think they came to this conclusion perfectly reasonable, I mean it got published and anything, that these data are better fitted by a repair saturation model than the linear quadratic model. So again, it's evidence, it's further evidence that these larger dose fraction sizes, then maybe LQ is not all it's cracked up to be. So no, let's just not accept what Brenner and Brown and everybody is saying, that we should just go home and believe LQ, when basically the people that invented this concept are raising flags over it, as you've seen in many articles in the Physics Journal. And of course, how can this make a difference? Why should it make a difference? Well, Howard Thames went on and looked at these so-called high-dose log linear models, predicting higher ISO effect doses than the LQ as the curve goes more and more linear at high doses per fraction. And they asked a very simple question: at what dose does this divergence between these two models potentially become significant? You know, earlier on I said it's going to be above 6 gray per fraction. Well, you know, is there any evidence that this divergence might be happening at even lower doses per fraction? And they looked at 3 tumor sites here, the breast, the prostate, and the lung, where we're doing a lot of hypo-fractionation and SBRT, identified the relevant alpha over beta values and doses per fraction for both the tumor and the normal tissues. And they chose those high-dose log linear models consistent with the parameters and estimated what size of dose per fraction where you would get 10% or greater disparity between the predicted ISO effect doses from both the LQ and the high-dose log linear. And then the obvious question is, what doses were you actually using clinically, and does that correspond? And they saw here that in breast, between about 2.7 3.3, you've got LQ predictions of doses that are approximately correct for the tumor and toxicity, but too low for higher doses per fraction, more than 6, right? Remember, breast is one of the targets that we're doing potentially higher doses per fraction now. For the prostate between 2.7 and 3.1, your LQ predictions of the ISO effects are approximately correct for tumour and toxicity again, but too low at high doses per fraction greater than 4, right? Well, so there you go. And again, this might undermine a little bit the extent to which we might think we're going to get a gain from hypofractionation. But I mean, all you've got to do is run the calculations, and it's damned obvious that we should be hypofractionating prostate cancer now. What's the alpha over beta of prostate cancer? 1.5. I mean, for goodness sake, it's a no-brainer. For lungs, your dose per fraction is less than 10 gray. So you've got LQ predictions of ISO effect being approximately correct for the tumour at early tox, but too low for the high doses per fraction more than 12. So in all of these cases, and this is looking at the clinical data, it is looking as if, contrary to what Brenner is saying, that we've got to start being careful when we push these doses per fraction up around 10, 12 or 18. But as I said, the most important thing earlier is that we are on the okay side of being safe. LQ is always going to estimate a lower tolerance dose compared with what might be the reality. So if you stick with the LQ, you're going to be on the safe side in your estimation. So finally, it's obvious we've got lots and lots to do over the next 15, 20 years. I mean, with the physics leading the way, we've got the superb dose distributions, the quality assurance, increased consequence of having to do that might be a financial issue. Optimizing the image guidance, that's huge now. You know, we can put the dose where we want it, we just need to know where to put it, and so we need better imaging. Rapidly delivery, look at maybe the possibility that we have interesting effects occurring at high dose rates, and papers have started to appear on that. From the biology leading the way, can we exploit that low tumour alpha over beta clinically? And you can see how this is driving more and more clinical trials of SBRT and hypofractionation. Always asking whether your LQ might be still good for the high doses per fraction there. And what about vascular and immunological effects? And I know that's what Brian Marples and Steve Brown are going to be talking about. So